So we want to look at polynomial inequalities, and that's what we have right here. We're used to seeing inequalities, but they've been linear in the past, and mostly the difference is uh, the with polynomial inequalities you have exponents that are not 1. So you have x squared terms or x cubed terms. And so we would like to solve this and find out those numbers that make this inequality true. Now, so what that means is what numbers can we plug in here and here to make this side less than 0. All right, so we can solve this problem algebraically, and we can also consider it graphically. We're gonna solve it algebraically first, so you can see the process, and then we'll talk about what that means in terms of the graph, because the graph can help us with these polynomial inequalities. Basically, to solve a polynomial inequality, the first thing you've got to do is you want to find the zeros. And you remember that the zeros of a polynomial are the numbers where the thing equals 0, right? Now we're interested in when it is less than 0, but the first thing we're going to do is find out when it equals 0. So that, of course, means we're going to take the polynomial, set it equal to 0, and solve. And so we remember that to solve a quadratic equation, we can choose factoring or the quadratic formula. We are going to solve this one by factoring, because it factors easily, and it leads to the two zeros of 5 and -1. Okay, so that's where this equals 0. Now graphically, let's just take a look at the graph while we're here. Graphically, what that means is that's where the graph crosses the x-axis. Okay, so where the graph crosses the x-axis is what we just found, right? That's what the zeros are. So that's our first step. Now what we're going to do is, there's several ways to do this. Let's use a number line approach. And basically what this means is you're going to create a number line, and on this number line you're going to locate your two zeros. So there's -1 and there is 5. Now notice on this number line we have now divided the number line into 3 sections, right? The zeros divided into 3 sections. It turns out the solutions to our inequality are going to be all in one section or another. Now it could be in a couple of the sections, but basically what that means is it could be possible that every single number in that interval from -1 to 5 is a solution. It's not possible that 0 is a solution but 1 is not. What we know is, and we'll see this graphically, we know that everything in a given interval will either be a solution or not a solution. So what we're going to do is we're just going to pick some test values in each of these intervals, and we're going to test to see if they're solutions. Use test values. So all that means is pick a number in each of these regions. So maybe I choose -2 in that region. And the question is -2 a solution? So I can plug it into the inequality and see if it's a solution. And that, of course, is going to lead me to what? 4 plus 8 is 12 minus 5. That's it. I don't really care what the number is exactly. I just care that it is greater than 0. Right? So if I plug in a -2, I'm going to get out a number that's greater than 0. Now, if I plug in a -3, something there, or a -4, I don't know exactly what I'm going to get, but I'm always going to get something greater than 0. So that means this interval does not contain solutions because it's greater than 0, and we want to find out when it's less than 0. Okay, So now pick a value in this second interval. 0 is in this second interval. That's always a good one to choose. Plug 0 in. So you're going to get a 0 minus 5. That's a minus 5. Again, you don't really care what the number is. You just care that that is less than 0. So 0 is a solution. So that means all of the numbers in that interval are a solution. And you could test it, right? So pick another number, just for instance, say a 1. Plug it in to the inequality. You're going to get 1 minus 4 is a minus 3. Minus 5 is a minus 8. Again, less than 0, a solution to the inequality. So finally, we can pick a number here and plug it in. Is 6 a solution? Well, you're going to get a 6 squared, that's 36. Minus 24, that's 12. 12 minus 5 is 7. That is greater than 0, and that is not a solution. And so we have found that our solutions are in this interval from minus 1 to 5. Now we don't include minus 1 to 5, minus 1 and 5 or 5, because remember, that's where the inequality equals 0. And we want just strictly less than. If it was less than or equal to, then we would include the endpoints. But there it is. Our solution, as demonstrated by this number line method, is simply, if we put it in interval notation, everything from minus 1 to 5. And that's the algebraic approach. And there are some other little tips and tricks that you can pick up and we might explore, but that's the bare bones approach to solving a polynomial inequality. Now I want you to glance real quickly over at the graph. Where are these intervals on the graph? Let's chop up the graph based on those intervals. So let's see, here's minus 1 and here's 5. So there's the first, the left interval, there's the middle interval, there's the right interval on this number line, right? And so basically it's very simple. Graphically, when I want to figure out when an inequality is less than 0, what I'm trying to figure out is when is the graph underneath the x-axis? When does it, that would reflect negative y values. But in simple terms, if you want to figure out when it's less than 0, what you want to figure out is when does the graph dip below the x-axis. If I were trying to find when it was greater than 0, I would be trying to identify where the graph is above the x-axis. And then of course where it equals 0 is where it is right on the x-axis. So graphically, we knew before going in that, if this is my inequality and I'm looking at the graph, I say, hey, I want to figure out when it is less than 0. So I just simply want to know, over what interval is it below the x-axis, and that's from minus 1 to 5, not including minus 1 to 5. So we would have the same solution graphically as we do algebraically. And so we have what we need there, and we can proceed.